Good evening to everyone. We are here for the 11th session of Astro Adda, organized in collaboration with the Public Outreach and Education Committee, Astronomical Society of India, and Nehru Planetarium, Nehru Memorial Museum and Library. We are here today to go way back into the beginnings, evolution of the universe. We are very happy we have with us Professor Tirthankar Roy Choudhary from the National Center for Radio Astrophysics, which manages the GMRT, the Giant Meter Wave Radio Telescope, the largest telescope with meter wavelengths, and an institution which is also taking us forward into this the next giant leap in radio astronomy, which is the SKM project. And Professor Tirthankar Roy Choudhary is is going to kind of walk us through some of the very early moments by kind of looking at the cosmological footprint of hydrogen and telling us about the very first early stars. So I hand over to you, Professor Tirthankar. I have to put your yes. So we have I have it's your presentation is now visible,
Okay.
and huh, just to tell all the viewers that the questions would be taken up towards the end, but you are welcome to put them in the chat box. Over to you.
Thank you, Ratnashri. Thank you for organizing this nice Astro Adda session. So, what I wanted to tell you all about is about the first stars, the very first stars in the universe, and how are the astrophysicists and cosmologists planning to observe them and learn about them. So, but before we really talk about the first stars, let's learn a bit about our universe in the cosmological sense so that you understand why the first stars are important and how they fit into this grand picture of the evolution of the universe. Now, let me start with something which is important, particularly in cosmology. So, what is the main ingredient in observing the universe? As of now, most of the information we have in cosmology is through telescopes which detect light. By light, I mean radiation from distant galaxies. These galaxies come in various types and shapes and sizes, but the basic idea is to detect them using telescopes. Now, one thing you would realize is that the more distant these galaxies are, the earlier would the light be emitted. This is just because of the fact that light travels with a finite speed. So, the moment we start observing very, very, very distant galaxies, we start to learn about the state of the universe at early times because the light would have started very early from those galaxies to reach us today. And of course, we observe these galaxies at different wavelengths or frequencies, and that makes the information very rich. I've just shown you one nice picture taken from the Indian Astronomical Observatory, Hanley, their gallery. So you can see a very nice picture of this telescope in Ladakh with vast universe upwards. So this is our universe, but let us come to cosmology now. What do we know about cosmology? We know a lot, and one thing which sets the modern cosmology is the fact that distant galaxies are moving away from us. And this gives rise to the concept of an expanding universe, which many of you would have heard about. This is kind of known as the Hubble-Lemaître law. Now, it's not only that the distant galaxies are moving away from us, they are moving away in a very particular way. The speed of recession is proportional to the distance to the galaxy from us. That is, a galaxy which is, say, twice as far away from us is moving away with twice the speed. This is the proportionality. So this is very important in setting up the mathematical equations which describe the universe. But before going into more details, let's understand one more concept that is a direct consequence of the expansion of the universe, and that has to do with redshift of light. As the universe expands, so does the wavelength of light as it kind of propagates through this vast universe. For example, if you have a light which is emitted at some time, earlier time, with this wavelength, by the time it reaches us, by the time we observe, the universe would have expanded because time has elapsed. So the wavelength of the light has become, you can see, larger. Okay. And wavelength becoming larger means it's moving towards wavelengths which are redder compared to the wavelength which it was emitted with. So this is called the redshift of light, and this plays a vital role in cosmology. The way to understand this is that the size of the universe is characterized by something called the scale factor, which I have written as A, which is the function of cosmic time t. Now, the way it is defined is that A gives you the size of the universe compared to the present size, which means A today is exactly 1. Now, the wavelength of the light actually increases exactly like A increases. So, if the size of the universe becomes double, the wavelength will also become double. And I've just written some formulae. You don't have to really go through them, in details. But what you have to understand is that the redshift of the light indirectly tells us what was the size of the universe when it was emitted. So imagine light coming from a very distant object. So that means it was emitted at very early times, which also means that when the light was emitted, the universe was smaller than what it is today. So that is why the light we receive will have larger wavelengths. And by comparing this wavelength with, for example, wavelengths in the laboratory, we can figure out how small the universe was when the light was emitted. And this is extremely important in cosmology. This essentially tells us about, when we see a galaxy, when we observe a galaxy, we immediately know how small the universe was when the light was emitted from that galaxy. So again, let me emphasize, the earlier the radiation is emitted, the more is the increase in the wavelength, more is the redshift. So higher redshift means we are looking at an earlier time, earlier phase of the universe. Okay. So let us come back again to the universe we know. So as I said, at early times, the galaxies were closer to each other. Now, if the universe was a movie and I could run the movie backwards, I could immediately see that the universe actually would have begun from something which is very small size. Okay, let's say a point. Now again, this is very, philosophically people have debated about it. How can all matter in the universe be kind of put in a point and so on? Is there any problem with the theory and so on? So in fact, this is something which is kind of somewhat disturbing to many people, because when the size of the universe becomes zero, all physics laws kind of tend to break down. However, Einstein's general theory of relativity, which is what we use to study this cosmology, the expansion of the universe, and so on, it predicts that such singularities are inevitable. And two of the examples where these singularities occur are black holes and this Big Bang, the early stages of the universe where everything kind of collapsed to a point. Perhaps the solution to this, avoiding the singularity, lies in the quantum theory of gravity, which we don't yet have. But currently, if you just follow general relativity, such singularities are inevitable. And this was essentially a lot of work was done by Hawking and Penrose, whose photos you can see here. And of course, Penrose, as you know, is currently in the news because of the Nobel Prize. Again, which is because of his work on singularities, but not exactly Big Bang, but black holes. But you can see the connection between all these things. Okay, I mean these are all Einstein's general relativity, which is doing all these things. Okay, let's come back to our universe again. Now there are, I mean, we know that the universe is expanding, so it would be smaller at early times. What else do we know? We also know that the early universe was homogeneous. So when I say I know something about the early universe, that means I'm definitely receiving some light which started very early in the universe and it got redshifted. I mean, the wavelength increased and it's reaching today. We know this actually from the observations of what is known as the cosmic microwave background radiation, or CMBR. You can think of it as the light left over from the Big Bang. It's a direct prediction of Big Bang. So Big Bang theory will have this cosmic microwave background radiation, and it's there. We have observed that. Okay. Now, this cosmic microwave background actually reflects the state of our universe when the age of the universe was something like 400,000 years. So, if Big Bang is the starting point of the universe, t equal to 0, time equal to 0, then the CMBR reflects the state when the age was 400,000 years. Just to set the context, the age of the universe today is approximately 14 billion years. So you can see the CMBR actually is telling us about the universe, which was kind of infant. Okay, it's really young. If we are interested in the redshift was 1100 of that order, which means the universe was like 1100 times smaller than what it is today. Okay, so that is something we know. And when we observe this cosmic microwave background radiation, no matter which direction we look at, it looks the same. So, I mean, that is actually shown here. Imagine this to be the sky, and no matter which direction you look at, it gives the same amount of signal. So, that is why we know that the universe was really smooth, or what we call homogeneous, at those times. In fact, CMB also is very important in cosmology. It was discovered in 1965 by Penzias and Wilson, somewhat accidentally, but very important discovery, obviously. But remember, this was also kind of complemented very nicely by the theoretical work by George Gamow, Alpha, and Herman. I mean, they had done the calculations and found out that such a radiation should exist from Big Bang. So, in fact, their calculations helped a lot in interpreting the signal Penzias and Wilson had got, because, I mean, when they were they were finding this excess signal. I mean, initially they had no clue where this is coming from. So, this gives us a kind of hint, or a very good indication of how the field, any field in science moves. It has to be a very nice combination of observations and theory. Okay, so that's something to keep in mind. Again, this CMB has a very good connection with Nobel Prizes. In 1978, Penzias and Wilson got the Nobel Prize because of this discovery of CMB. Now I said it is very smooth. Is it really smooth? Now, if you look at the CMB very carefully with very high resolution, which is possible nowadays, you see it's really smooth, but there are fluctuations. There are very I mean, tiny fluctuations. How small? Small means one part in 100,000, 10 to the minus 5 in mathematical sense. Okay. So these fluctuations do increase, and we have observed them. The CMB experiments have gone and observed them. How did they arise is something which we don't know, because, as I said, if you go very early in the universe, we struggle with our laws of physics. I mean, we really don't know how to apply them. Maybe some quantum effects played a role or something. So yeah, I mean, we don't know, but let's say they arose because of some reason, and we had this one part in 100,000 fluctuations in the CMB. Again, this is also very important because this also led to another Nobel Prize in cosmology, and that is more recent, I mean, relatively recent, 2006. A satellite called Kobe in late 80s, 89 or so, was launched to actually observe these, try to detect these fluctuations. And these two people, John Mather and George Smoot, won the Nobel Prize here. And if you just read the citation for George Smoot's case, you will see it's talking about the instrument that measured small temperature variations of the microwave radiation in different directions of the sky. And so this is basically it. I mean, the CMB is smooth, but there are tiny fluctuations, and you really need a very sensitive telescope or a satellite to observe. And of course, after Kobe, we had two more satellites, WMAP and Planck, did fantastic jobs to tell us more about these fluctuations, and we have very good quantitative handle on these fluctuations and a very good theoretical understanding of this. Let's go ahead. So that was the state of our universe, infant universe, 400,000 years old. What about the present universe, this 14 billion old universe? So now let us do some observations of this universe around us. The easiest thing, as I said very early in the talk, is through observing galaxies. So you go, take telescope. I mean, you need really big telescopes. Very sensitive telescopes. But you go and observe galaxies around us. And you observe the galaxies and then kind of make some plots. Okay. So, for example, this is a plot from one such survey called Vipers. And each point here corresponds to a galaxy. Now, you can immediately see, just look at it visually, you can immediately see that galaxies are not kind of randomly distributed. Okay, then there is some structure in the distribution of galaxies. By this I mean that we would see regions where there are kind of more galaxies. There is a lot of galaxies, a collection of galaxies here, a lot of density here. And then there are regions which are kind of voids. There are absolutely no galaxies in this region. And then if you look at like two very high density regions where there are a lot of galaxies, they're kind of connected by some filament like thing. You can see one filament very nicely here and so on. So it's a rich structure in the distribution of galaxies. You can see these filaments and voids and sheets. It's popularly known as the cosmic web because of the way it looks like. So it's very interesting, and the richness of the structure is not the kind of tiny fluctuations we see in CMB. In CMB, we say the universe is very smooth and very small fluctuations. What we see around us when we observe galaxies, so which essentially tell us about the matter distribution, it's not at all smooth. It's very patchy. There is a lot of structure. There's a lot of richness in the structure and so on. Now, this is the problem of what we call the cosmological structure formation. If you say that the universe was very smooth with very tiny fluctuations at early times, how did we go from that picture to a picture where we see lot of structures, this richness in structures? So the universe evolved from 400,000 years to this 14 billion years, and somehow all these structures grew. If the structures did not grow, there wouldn't be galaxies, there wouldn't be all these solar systems or planets, and we wouldn't be discussing all these things. So it's really important for us to understand how these structures formed. And this field is known as the study of large-scale structure formation or cosmological structure formation, or just say structure formation. Okay, so how did the structures form? Mathematically, you can treat this as kind of initial conditions of your problem, and then you solve your equations and find a solution which will give you the state of the universe, which is this. Okay, so this is the mathematical way of stating the problem, but you understand what I am trying to say here. In fact, this is last year's Nobel Prize for Physics, and 3 people won it. 2 people won it for exoplanets, which are very interesting field. But the third person, which is James Peebles, he in fact won the prize for theoretical understanding of what we call physical cosmology, and a lot of that had to do with this cosmic microwave background, the theory related to it, the fluctuations there, and how they evolve and give rise to all the structures we see around us today. So that is the importance of James Peebles' work, and it's now you understand the importance that the Nobel Committee also recognizes this kind of the field of study. Now, if you just ask how did the structures form, I mean, they were so small fluctuations. How did they grow to give us such nice looking structures? Now, this actually is not very difficult if you think about it, and that has to do with the concept of gravitational instability, the way gravity works. So, what has been shown here in the top panel is, let us say, the density of the universe in some one direction. So, this red curve shows the density. The density goes up and down, but it goes up and down by a very small amount. So, this, let us say, I mean, think of it as the state of our universe during the CMB. So there is a small region which is slightly overdense, slightly more matter, and then there is another region B which is slightly underdense, and then there is something which is overdense. This would be these fluctuations in the CMB will be 1 part in 10 to the 5. Of course, for drawing, we have just exaggerated it a bit, but think of them as very small fluctuations. Now, the peculiar nature of gravity is the place where there is more matter than the surroundings, that place will start attracting matter. This is the fact that gravity is an attractive force, okay, and it is proportional to the mass. So this point A has slightly more mass than the nearby area, so it will start attracting more matter towards it. Where will it get the matter from? It has to get the matter from, let's say, point B, which has less matter, so it is not able to attract the matter so strongly. So matter will then start going from B to A. And that is what is shown in the lower panel. The moment you have a slightly overdense region, that region will grow and become more and more overdense. And just to compensate for that, regions which were underdense, slightly underdense, will become more and more underdense. Okay. So you can see A has become more overdense, B has become more underdense, C has become more overdense, and so on. And these orange arrows tell you how the matter is flowing. So the matter is kind of flowing from underdense regions to overdense regions. So gravity, its nature is to amplify fluctuations. So that is how essentially structures form. But the actual picture may not be that simple also, because this can be kind of compensated a bit by the expansion of the universe, because expansion is trying to take matter away from each other. So there is this competition all the time. Now, yeah, so this has to be then worked out mathematically. And of course, this is not the time to go into mathematics. But in principle, you can solve the equations. Okay, so you solve Newton's laws, which tells you that the acceleration of matter is driven by the gravitational field. And the gravitational field itself is determined by the matter distribution in the universe. Of course, the equations which I have wrote here are simple equations, but they have become more complicated because of expansion. There will be some additional terms which are put in, and so on and so forth. But in principle, this problem can be solved, but it's a very complicated problem, because you think of it, I mean, you're solving it for a universe where there are so many points, so many kind of matter particles, and so on. So it's not like you can solve it using pen and paper very easily. So this is where computer simulations play a big role. So the fact that inhomogeneities grow, these structures grow because of gravitational instability, is very well probed by computer simulations. This is one such example. What is shown here is a kind of box. Let's say this is some volume in the universe. At very early times, the universe looks homogeneous, which is this with very tiny fluctuations. So maybe you won't be able to even see the fluctuations because they are small. And this is actually resembling a kind of realistic universe. And then it evolves. It evolves this way. you come to the end of the first row, then you come here, and then it keeps on evolving as time elapses, and then you keep on evolving. And as you evolve, you can see the picture changes. It was very homogeneous at early times, and you see at some point you see these nice structures forming. You see these very high density regions, and you can see all these filaments all over the place. And by the time you reach the present universe, so this is the state of the universe today, you can see all these very high density regions, and then there are these all these filaments connecting the exactly the way we see in the observations. Okay, so it turns out that when we actually put all the equations and everything we know about the universe in the computer, we seem to get answers which are correct. And that's a very good success story for today's cosmological models and cosmology theory, that it can actually explain the formation of structures. In fact, people went ahead and tried to do real comparison with galaxy surveys and simulations, and this is one such picture which has been shown here. These are kind of slices from galaxy surveys. These are kind of slices from simulations. This was done, I mean, quite some time back using Millennium simulation, and you can see visually they look very same. Of course, when we actually match the models with observations, we don't do it visually. You need to do really good statistical models and proper mathematical way of doing things. And it turns out that the picture which I showed, the story which I told, actually matches the observations quite well. In fact, all these, the CMB, this formation of structures, have now led to what we call the standard model of cosmology. It's also, I mean, it's the name of the standard model of cosmology is called lambda CDM. Lambda basically because it's driven by dark energy, and CDM stands for cold dark matter. So it's also driven by dark matter and dark energy and so on. So all this picture has been set up, and it is essentially kind of determined by some parameters, okay, which values are now measured from observations. You don't have to really go into the details of the parameters, but this is just to give you a feel that we are in an era where all these parameters are measured to a very high degree of precision. Okay, we are living in an era of precision cosmology, which essentially tells us that we know a lot about our universe. That doesn't mean that we know everything about our universe. There are issues which have to do with nature of dark matter and dark energy. And there is something which is coming up in recent times, and that has to do with the Hubble tension. I'm not going to go into these details because I want to get back to the topic of today's lecture, that is the first stars in the universe. But before doing that, I wanted to set up this basic framework of the standard model of cosmology, this expanding universe, this early smooth universe, and then growing of these structures and these very rich structures we see around us today. Now, if you now go and just summarize this story, what I told you is that at very early times, we have these small fluctuations, treat them as initial conditions, let gravitational instability play a role, and you form all these large scale structures. These have been also verified observationally because we know the initial conditions from CMBR. We know this large scale structure from galaxy surveys. And galaxy surveys, of course, we look at the nearby galaxies, but we are also looking at very reasonably and very distant galaxies. And we have gone up to kind of times of our universe when it was only billion years old, 1/10 of its size. Okay, so if you think of this CMB as infant universe, we are already also looking at a kind of the baby universe, which is kind of 1/10 of it today's age, and the picture seems to be okay. It's matching, but there is still a range which is between this 400,000 years, the CMB, and the range where the galaxy surveys has reached today, that is the billion years. So this whole time range is kind of yet to be observed, or maybe we are kind of slowly started to observe them. Okay, so this gray region which I've shown here is still not accessible observationally, and this is often called kind of final frontier of observational cosmology, because this is the phase which we haven't accessed using our telescopes. and it's very important because unless we see what happened here, the story is kind of not complete. We have seen the very early times, we have seen the late times, but what happened in the middle? So one really wants to see that. And there is one very crucial reason why we see, because remember, during the CMB, the universe was very smooth. There were no galaxies or something. And then suddenly we see all these galaxies around us today. So it's natural to ask, when did these first galaxies and the stars formed? And this is the era during which they formed, falls bang in the middle of this kind of gray region, okay, which is not observed directly as yet. So that is why people are so excited to try to go and observe the first stars. Because once we do that, we think that a large part of this missing story will get completed. Okay, and it will tell us about what was the nature of the first stars, were they like same like the stars we see around us today, or were they very different? And then if we go and see first generation of stars and then the following generation of stars and so on, we learn a lot about how the universe evolved. So it's like the growing of this baby universe to what it has become today. Okay, so it's very good if we could kind of complete this whole picture observationally, and at the same time like through theoretical models, because they go hand in hand. So this is why first stars and galaxies are important, and that is why kind of I'm talking to you about these first stars in the universe, and many people are very kind of excited about these. Now, how do we plan to observe these first stars? One way is to make very sensitive telescopes. Why? Because the first stars would have formed very early, so we can only, I mean, the light would have taken a lot of time to kind of has to travel a lot of distance to reach us. So they will be kind of faint. Okay, I mean, because by the time they reach us, the light, the flux, or what we observe, would get diluted quite a bit. So we really need very sensitive telescopes. And a lot of telescopes, in fact, are being planned. And let me just highlight two of them. On the left, you see a satellite which is named as the James Webb Space Telescope. So, I mean, people who are familiar with the Hubble Space Telescope, or the HST, can think of this as a kind of upgraded Hubble telescope, or a much better version of the Hubble Space Telescope. So this JWST is supposed to fly, let's say next year or within a year or two. I mean, probably the timelines have kind of changed because of this recent pandemic or so on. But let's say it will fly very soon. Okay. So one of the science cases for this telescope is to go and observe these first stars. Okay. So that will be kind of direct detection of these first stars. The another way to detect these first stars is again through telescopes, but these are ground-based but huge telescopes. So if you are in the ground, you can make very big telescopes. If you are sending satellites, you really have to kind of cut down on the size and so on. So this is an artist's impression of one such telescope called the 30-meter telescope, and there are similar such telescopes being planned, but 30-meter telescope is important for us Indians because India is a partner in this project of making the 30-meter telescopes. It will come within a decade or so. Okay. Of course, these are ways to detect the first stars directly. But what you would realize is that if you have, like, let us say the first generation of stars, not all of them will have the same brightness. And what would happen is these telescopes will preferentially probably tend to detect the brighter stars first because they are easier to detect. So there will always be this question whether the stars we have detected, are they kind of the faithful distribution of the underlying population? Or, I mean, there are a lot of faint stars which are there, or faint galaxies which are there, and they are kind of got, I mean, we didn't detect them, but they are there. So maybe we are missing a lot of them. So these kind of questions will always arise with these telescopes which are trying to detect the first stars directly. So it is always good to have a complementary probe. Okay, and that's something which I want to discuss for the rest of the presentation. This alternate method has to do with hydrogen. Now, hydrogen is the most abundant element in the universe. It is just a proton and an electron kind of going around it. Okay. If you kind of ionize the hydrogen, if you kick the electron out, then it is just a proton. If the hydrogen is neutral, then as I said, it's a proton and the electron bound together. So it's the simplest of the atom you can think about. And as I said, it's the most abundant element in the universe. The galaxies are surrounded by hydrogen. And you can ask the question that once you start forming stars, there is a possibility that they will start affecting the hydrogen surrounding them. So, is it possible to infer about the stars using this hydrogen? And the answer is yes. In fact, there are several methods of inferring about the first stars using hydrogen. And I am going to talk about one of them, and most probably it's the most promising way to detect this hydrogen and learn about the first stars. And that is through something called the 21 centimeter radiation. What is 21 centimeter radiation? So for that, let's think about this hydrogen atom. There is a nucleus at the center, and which is essentially a proton, and then there is this electron, which is a much smaller version, and maybe it's just going around this proton. Okay. Now, what happens is these particles, these protons and electrons, they have something called spin. This arises because of quantum mechanics. So this spin is not like the earth spinning or something. This is a very, very strange kind of property of particles, and this can only happen in quantum mechanics. There is no classical analog of this spin. Now this spin, what can happen is this spin of electron and proton can either be aligned, they can be in the same direction, or they can be misaligned. Okay, so the proton spin points this way, and the electron spin points the opposite way. So there are these two possibilities. And if you can flip the spin, suppose the system which was initially at this state somehow goes to this state, that means the spin flips. What happens is there is a small change in the energy of the atom. And this small change of energy is compensated by a radiation coming out, or what we call a photon coming out of the system. This radiation will have a very particular frequency. It will have a frequency of 1420 megahertz. The corresponding wavelength is 21 centimeter, hence it's called 21 centimeter radiation. So if you have hydrogen, there is a chance that the electron will flip its spin and will emit this radiation. The opposite can also happen, that some radiation may come and the electron can absorb this radiation and its spin gets flipped. So it can absorb or emit this radiation, but whatever happens will happen exactly at this wavelength, okay? The 21 centimeter wavelength. Now that is the first thing to understand, that there is this 21 centimeter radiation of hydrogen. The second thing, which is obvious, but let me just emphasize, is that this is possible only when the hydrogen is in the form of an atom. It's neutral, okay? Now suppose somehow the electron gets knocked out of the hydrogen, so hydrogen becomes ionized, then this transition cannot occur, okay? This will only occur when the spins, these two are together, and the spin of one particle knows about the spin of the other particle, so to speak, okay? So once the electron dissociates from this atom, there is no 21 centimeter radiation. The 21 centimeter radiation will be there, or the signal will be there, only when this hydrogen is in the atomic state. And that's going to play an important role, which I'm trying to show here through this cartoon. So let us imagine, in a cosmological sense, there are a lot of these hydrogen atoms, all neutral, and all are kind of emitting 21 centimeter radiation. And we are somewhere, we have our telescopes pointing towards all these atoms in some direction, and we are observing them. So neutral hydrogen atoms emitting 21 centimeter radiation, nice, okay, picture. Let's say the first stars formed. In fact, that would be the case before the first stars would have formed. All this hydrogen would be emitting this 21 centimeter signal. Now, let us say the first stars form, the first galaxies form. So, these galaxies will emit radiation, and the radiation will contain photons which have wavelengths, which have energies which can knock this electron out. Okay, so the electron is bound, and if you give it an energy larger than what is known as the binding energy, it will just get knocked out. So if you give it, if you hit it with a photon having large enough energies, the electron will just dissociate. Okay, this is something which is similar to photoelectric effect, which many of you would know. This is known in the astrophysical case, this is known as photoionization. You are ionizing the hydrogen using photons. Now, the moment you ionize, let us say these three hydrogen atoms, the electron is gone. So there's no electron, the proton is just this alone. So now, earlier I was receiving 21 centimeter radiation from these three atoms, but the moment a star forms, there's no 21 centimeter radiation here. So I won't see any signal from these places. I may see signal from this place. Why? Because this atom is probably far away from the star. So the starlight could not reach and kind of dissociate this electron. So now you see the picture, what's going to happen. The moment the stars form, the region around them cannot show 21 centimeter radiation. So this place will be devoid of this 21 centimeter signal. If you now go to places which are far away from the stars, those places will show 21 centimeter radiation. So suddenly the picture will become very complicated. There will be places of the universe where you will get 21 centimeter radiation, and then there will be places where you won't get 21 centimeter radiation. Places from where you don't get 21 centimeter radiation most likely are places where the first stars have formed, and the other places where you are getting the radiation from are probably places which are far away from the first stars. And this is the idea which we are going to use to learn about the first stars. We are not going to observe the first stars directly. We are going to observe the hydrogen and the 21 centimeter radiation from them. And that is the beauty of this work. And let me just go to some kind of theoretical predictions here, which we are doing now. As I said, this is still not kind of observed, so to speak. We are reaching there, and I will talk a bit about it. But currently, we have some idea about how these things may happen. And what I'm going to show is a prediction from a model which we have been working on. So this is some theoretical work. And if any of you are interested, you can just kind of download the code which has been used to generate what I'm going to show now. And this is a code which is developed by us. It's called script. I, of course, won't have time to go into the details because that will need a lot of mathematics and background. But what this code will show you is that this is the state of the universe at very early times. So imagine this to be like a slice of the universe, a two-dimensional slice at very early times when the first stars did not form. And this is what you will see as 21 centimeter. Now, the moment the first stars form, what will happen is, this is the place where some stars have formed. These are the places where the stars have started forming. And you can see those regions have kind of become black, which means these places have got ionized and we are not receiving any 21 centimeter signal from there. Other places are still emitting 21 centimeter signal because no stars were formed here. Okay. And now if I evolve in time, you can see these regions are growing because more and more stars are forming, and then there are other regions which earlier did not have stars, now have stars. Okay. So remember, I'm not observing stars, I'm not showing you stars. What I'm showing you is neutral hydrogen, but just by looking at this 21 centimeter from neutral hydrogen, I'm able to make out where the stars would have formed. So now if I show you this picture, you will be immediately able to tell me that, okay, these are places where the stars have formed. Maybe this place has more stars than this place, and so on and so forth. So this is the power of using this 21 centimeter. And if I just evolve in time, you can see the picture, the black regions growing more and more. And now you see the black regions have grown, and these individual black regions are kind of overlapping. Earlier, these two regions were kind of two small isolated regions, and now they have started kind of overlapping with each other. And soon you will see all these regions which are isolated start overlapping. So it's basically telling you that more and more and more and more stars and galaxies are forming. And of course, all these models are done using what we know about the stars and the galaxies and so on. And if I change the nature of the stars and the galaxies, this picture will change. So the hope is to compare this picture with observations, and through that learn about the first stars in the universe. And as I said, as I move ahead in time, these black regions grow, and at some point it completely ionizes the universe. So there's one thing you should know: we are living in a universe which is predominantly ionized. Of course, the earth is not ionized, or the solar system is not ionized. But if you go to the large scale matter field in the universe, the matter outside the galaxies, what we call the intergalactic medium, which forms the bulk of the universe, all gas there is highly ionized. Okay, this has a name. This whole process is called reionization. So this is called reionization of hydrogen, so on. And this reionization is a direct effect of the first stars. Okay, and that's what one is trying to observe. You can ask, what kind of telescopes do I need to observe this radiation? Recall the radiation, its wavelength is 1420 megahertz or 21 centimeter. But remember, this radiation would have been emitted very early in the universe when the first stars formed. So by the time it reaches us, the wavelength would increase. Remember the redshift of light, which I talked about? So the earlier the radiation is emitted, more is the increase in the wavelength. And the frequency, so which means the 21 centimeter will now grow in wavelength, and will go to kind of meter wavelengths and so on. Or if you think in terms of frequency, the frequency actually decreases. So what started off with 1420 megahertz, by the time it reaches us, will be something like 50 to 200 megahertz, depending on when the first stars form. Okay, so these are the kind of wavelength range which I have to tune my telescope to observe this radiation. If I tune my telescope to 1420 megahertz, the 21 centimeter, then I'm not going to observe these first stars, because the first stars, by the time they come to us, would actually the wavelength and the frequency would be shifted to something else. And that's why we have to go to the low frequency radio telescopes. Okay, now the low frequency radio telescopes are already doing some fantastic job, and there is one way to detect them, and this is something which I will discuss but in a very brief sense. uh, what we can do is we can actually work out the details of this 21 centimeter signal. And this 21 centimeter signal shows very nice structures. Okay, it show it first, I mean, so what has been plotted here is the amplitude or the strength of the 21 centimeter signal versus the frequency. So the frequency increases this way, this is the observational frequency, and hence the cosmic time also increases this way. Okay, so the signal, it seems, does very fantastic things. It goes down, goes up, goes down again, goes up. And all these things happen for a reason which we understand. Except that this signal is very difficult to observe. Now you see the most prominent feature of this signal is this, where it goes down and goes up. Okay, this is where the signal is most strong. And this happens exactly because at the time when the first galaxy is formed, as is written here. So the moment the first galaxy is formed, the signal will essentially show this shape, and there are telescopes which are trying to detect this shape. And this was kind of claimed a year back, maybe more than a year now, by an experiment called EDGES. Okay, so the EDGES claimed a detection of this 21 centimeter signal, and this is the signal they detected. Okay, this is very similar to the signal which I showed here. This was, of course, a theoretical prediction, and this is what they detected. Now, this signal has gotten into quite a bit of controversy because there are issues related to the strength of the signal. But this is something which has interested us. And this, for example, is something we are doing. We are making models to actually see if we can match this signal. There is no point in going to the details of the model, but we think that it might be pointing towards the early stars. Okay, so we are probably observing the early stars, provided the signal is real. So one has to really wait and observe the same signal using other telescopes to make sure there is no instrumental artifact or something else which is showing up here. So one has to be very careful before concluding anything. However, if this signal is real, we are observing the early stars. So this is some work which was done in our group, and we can tell now what would be the properties of these early stars. Okay, how different they would be from the present stars and so on. So, rather than making claims, let's wait for the signal to be confirmed. If it gets confirmed, we have a model which can explain this. Okay, we can do much more. I mean, we can actually go and try to make maps of this 21 centimeter signal. For example, let us say a galaxy has formed here. It will show very nice features around it in the 21 centimeter signal. However, when we observe using a telescope, the telescope won't show this nice looking signal. It will show something like this. So this is due to the telescope artifacts. Okay, but it is observable. And of course, remember, these are all theoretical predictions using our models, which I showed you earlier. But the hope is to go and observe them. And you can ask why haven't we observed them? We haven't observed them because the signal is very weak. The 21 centimeter signal is very weak. So you have to really wait for a long time before the telescopes reach that sensitivity. There are many low frequency telescopes which are trying to observe this signal. You can see one of them is the GMRT, the Giant Meter Wave Radio Telescope. As Ratnashri said in the beginning, that this is a telescope which was built and being maintained by the institute where I work, the National Center for Radio Astronomy, so that radio astrophysics. So that is NCRA, and so these are basically the nice dishes of the GMRT, which is trying to detect the signal. There are other telescopes. That one is LOFAR. This is in Netherlands, in Europe. And then you have MWA. That's in Western Australia. There was a telescope called Paper in South Africa. It's done its job and now dismantled. However, these telescopes have done fantastic job. They may not have the sensitivity to kind of detect the signal, but they have taught us a lot about how to go about detecting the signal. We probably have to wait till the next generation of telescopes come up. For example, one of them is the Square Kilometre Array, in particular the Square Kilometre Array Low, which will come up in Australia. This is, of course, artist impression. And one of the major science cases of SK is to detect this hydrogen signal and study about these early times when the stars were formed. There is another telescope which is being planned. It's called Hera. And here, I mean, its kind of only science case is to detect the 21 centimeter signal. This will come up in South Africa. Okay. Let me kind of end the talk by talking a bit about the Square Kilometre Array. Square Kilometre Array is again very important for India because India is a partner in this multinational project. So this is the Square Kilometre Array, which is going to be built by dozens of countries. I mean, and it is going to kind of enter into the construction phase within a year or so. It's essentially what you can think of it as the most ambitious radio astronomy project ever attempted. It will be built in kind of two parts. One part will be in Australia and one part will be in South Africa. The Australian part will be interesting for the science cases which I talked about, like the first stars. But the South African part will also be very interesting for other aspects of cosmology. But the square kilometer array is a very generic telescope. It will have a wide range of science cases, okay? Starting from the planets and suns to the early times of the universe, the cosmology, okay? So again, it will probably come up within the next decade or so, maybe 7, 8, 10 years. And as I said, one of the main science goals is to detect the signal from the first stars through neutral hydrogen. NCRA is a member of the India is a member of this collaboration, and the Indian participation is currently coordinated and led by NCRA, as I mentioned. And the GMRT which we have is often very useful to do tests which meant for SK. For example, GMRT may not be able to detect this 21 centimeter signal, but we can do experiments using the GMRT, which will tell us a lot about how to manage the observations and probably the analysis of the data. So once the SK comes up, we will be kind of ready with all the tools we have. So that is where the GMRT can play a big role, and that's something the Indian community is looking forward to. Okay, and that brings me to the kind of summary of my talk, and the main points which I want you to take home is that the first stars are the kind of final frontier of cosmology or observational cosmology, and they can be studied directly, but they can also be studied through signal from hydrogen, which is a very promising probe of the first stars. Now, this 21 centimeter signal of neutral hydrogen will open a new window in studying the first stars. There are already interesting results from the operating telescopes, but we are really looking forward to the square kilometer array. As I also wanted to kind of highlight is that observations and theory have to go hand in hand. And we already have very good progress in theoretical modeling also, but we still need to make much more accurate and kind of efficient models, because without these models you won't be able to interpret the upcoming data. There will be humongous amount of data and information which are there. To interpret them, you will need very good theoretical understanding of the process. So both have to go hand in hand, and I'm glad to say that the Indian community is doing excellent work in both. Okay, so this is a very good time to stop. So I thank you all again for attending the talk, and let me stop here. Thank you, Vin.
Thank you, Tirthankar, for taking us through that really user-friendly walkthrough of possible signatures of the first generation stars through the absence of the 21 centimeter radiation. So that's very very interesting. I think what we will do is maybe go backwards in questions, and all of you who are there, you can now put your questions as text. There is Sandeep Dubey. I'm just trying to. Actually, Tirthankar, if you come out from your window of the presentation, come to the studio tab, you will be able to see that I am flashing the questions, so
Yes,
it will be
yes,
there.
I can see the question now. Yes, yes.
Yes, yes. So that's Sandeep Dubey wanting to know about.
So he's asking, how does the intensity of the 21 centimeter line change with passing generations of stars in a specific region in our universe? So of course, the intensity of the 21 centimeter line will be very high when there are no stars, because everything is neutral. The moment you start forming stars, the intensity tends to go down because there are less amount of neutral hydrogen, and so on and so forth. And at some point, you will completely deplete the universe of neutral hydrogen. The signal will go down further. So, very crudely speaking, the signal will essentially go down as more and more stars form. Okay, so this is the basic idea we have now. Now, of course, it is much more complicated than that in some sense, because some regions in the universe will form more stars than the other. So the signal will show very rich structures. And through those structures, we plan to learn about the first stars in the universe. But the crude thing is, more stars forming means the decrease in the 21 centimeter signal. Yeah.
Uh, Himanshu Chauhan was asking about. Let me just. I'm just trying to get his question earlier. Yeah. So he wanted to know about H alpha emission, and
Okay.
I was just actually, I mean, this. I was also wondering that, like, this probably is from the newer stars and nebulae and so on, where we observe
Yes.
this. But
Yes.
while he has asked this question, I was also about when there is this ionization taking place, the signature of that is also, I mean, possible to be observed,
Yes.
and what would be the possibility there?
Yes. So, yeah. So the point is, when ionization is taking place, what will happen is you have thrown away the electron, but this electron, there is a non-zero probability that electron will come back to the proton and recombine. That's called recombination. Now, it will recombine. When it recombines, it may recombine to a higher state of the hydrogen atom and then slowly cascade. So, as it cascades, it will give rise to various radiation. So one of them is this H alpha, Balmer alpha line, and then it can give rise to Lyman alpha and so on and so forth. The thing is, these lines are very easy to observe in stars, okay, where this thing is happening. I mean, as Ratnashri also said, this nebula and so on. This strength of this radiation in what we call the intergalactic medium or cosmological matter is extremely low. Why? Because the density of matter in the cosmological sense is much smaller than the density of matter in stars. So this probability of recombination, where you need two things to come together and recombine, it goes as like proportional to the density square, because you need two things to come together. And the moment you make the density smaller and smaller, the strength of the recombination radiation goes down drastically. So that is why we cannot really see all these lines, these H alpha lines or Lyman alpha lines, coming from the intergalactic medium. Okay, they are very prominent in stars and galaxies, so one can observe them, and there are ways to actually use them to learn about this reionization and the first stars, which I didn't have time to go into. That's happening now. I mean, I mean, people are observing these Lyman alpha and H alpha lines from galaxies at very early times and using them to learn about reionization. But that is something different from what I talked about, and that will require some more background, kind of, so to speak. So yes, so that's what it is.
Paras, he was earlier also asking whether the presentation could be shared with the participants. But he's also asking about possible projects to a physics undergraduate student. You were
Yes.
mentioning that code. Would there be
Yes.
any simpler explorations possible for students?
In principle, yes. So it depends on, okay, what kind of background you have and what kind of interests you have. One
Uh,
option is to, I mean, rather than using the code, what one can give you is kind of generate. For example, I can give you the box, okay, which will have the signal already put in. Now, I mean, just if I could go back to this presentation, and I didn't go into the
yes, yes.
details of the signal, let's say. So suppose this is the signal, okay? And I mean, this is what is given to me. And I want to learn about the first stars. So for example, one way of learning would be if I can, for example, measure the sizes of these bubbles. Well, I mean, bubbles, by bubbles, I mean these ionized regions, the absence of the signal, okay? Now there are very nice kind of strategies here. So suppose I give you this signal, can you tell me from this signal how many bubbles are there of what size? Now if you think, it's very easy to do visually. You will go and like count almost the bubbles and their size. But can you come up with a mathematical algorithm to actually work out the sizes of the bubbles and so on? Okay. The moment, if you think about it, it's not very straightforward to do that. So what the broad thing I wanted to say is that if I can give you all these data cubes, there are very nice things which you can do. I mean, this is just one example which came on top of my head, but one can define very nice kind of what I call kind of signal processing equivalent projects. Okay, you learn about the signal just from the box.
There's
And
some.
tell us. So that is something which we can kind of go ahead and define the project. But as I said, that may kind of depend a bit about on what the student is after. I mean, whether they want a more mathematical project or a more computational project or more data oriented project. And there are many such things which we
Yes,
can
yes,
define.
yes. There
So
were a good number of students who were in the Astro Adda group who were interested in taking up such projects. Some of them uh, uh, using Python coding and so on. So
ah,
perhaps this project is something which could be discussed. If you could give the material, we have these
yes,
two WhatsApp groups, and I
yes,
gave the link for one of the groups to for those students who are not already in the groups.
yes.
And maybe if it could be followed up over the next week by those students who are interested in doing such an exercise. So
No,
that
no,
is really
that's absolutely possible. That's absolutely possible. I mean, this code is essentially it's a Python. I mean, there's a
yes.
Fortran code which runs, but you have to interact with the code using Python. So
Would you?
any of you who are interested in Python can easily run this code and interact with the data there.
I'll
So
check with the students and see how much of momentum is there to do this. And if
absolutely,
they are taking it up, then I would request you to be in the WhatsApp group for a week or so.
absolutely, I will be
Running
happy
the
to do.
announcement. There is
Yeah.
a young student who is a school student, I think. So she's asking that if you could give her some advice as to what she should do for a career in astronomy.
Yes. Yeah. So the career in astronomy, I mean, the way in India, I mean, I'm assuming that when you say career in astronomy, you are really interested in doing a PhD in the field of astronomy and astrophysics, and then take it up as your career. So I'm really thinking in terms of the academic aspect of astronomy. So if you want to do that, I'm assuming you have to get into one of the PhD programs. Okay. So if you want to get into one of the PhD programs, that would be after your BSc or MSc. So after BSc, you can get into what we call the integrated MSc PhD programs. After MSc, you can go into the direct PhD programs. Now, for all of these programs, you need to get a very good handle on basic physics and also mathematics. What you will realize is whatever I have talked about, although I talked about in a very general sense, require a lot of physics. For example, this 21 centimeter radiation requires quantum mechanics. This computation of the signal will not only require quantum mechanics, but understanding of electromagnetic radiation will require understanding of what we call statistical mechanics and so on and so forth. Then the universe itself will you will need to know you understand the gravity, the gravitational force, preferably general relativity and so on. So there's a wide bit of physics which is needed. To do physics you will need to learn a lot of mathematics because that's the tool one uses, and preferably you have to complement that by computing, that's code writing, and statistics because you will do some comparison with data and so on. So, my suggestion is to do your physics courses very seriously during your BSc and MSc. You learn all the basic physics. If you get to do some astrophysics courses as electives or so on, very well. Not necessary, but it helps. But get the basic physics under control, and then it will be very easy to get into any of the PhD programs. I mean, preferably of your choice, and choose a field of study in astronomy. So that would be my advice.
Yes, and since the question was asked by a 11th grade school student, so do you, I mean, follow up the advice which was given to you for a possible future graph? And while you are in school, if you are interested in astronomy, try to learn through such for such available resources which are there. Maybe take up some simple projects, quantitative projects. We from our planetarium we have quite a lot of activities for school students, so I mean be there for those. We
Yes.
so maybe I mean I don't see further questions as of now. So Paras was asking about the presentation. That would be okay, right? We could share it with
Yes,
the
yes,
students
yes, yes. So
in WhatsApp in the WhatsApp group. Yeah.
Yes. So
So
how do I share? I will just upload in the
yeah,
WhatsApp group
if
or
you, yeah, when you are in the WhatsApp group, you could, I will just check with the students who are there, and if they are active, then I will ask you to come in maybe in the group, or I
just
could share it with them. So
just
I
let
think we are. Thank you so much for doing this. I mean, such a difficult area of study. You brought it out so beautifully for young students to get a feel about this.
thank
Thank you. Okay. What there is one question. I'm a little confused. What is it? Mm, latest methods to find out stars in naked eyes. I think probably. I mean, what you are talking of is by naked eye observations. What you can find out about stars. Something about the positional astronomy aspects, and maybe those which are variable stars with very like which have very bright variations. There are some possible projects. We will be talking about some of these in our planetarium sessions, so I hope you will were you also going to say something
No,
in
no, no.
this
I was just going to say that
context?
the planetarium is the right place to get these things.
Naked eye star projects. So
Yes,
yeah,
yes.
all right. So I think we will now close this session. Thanks so much for being there, and thank you all of
Thank
you
you,
for being there.
Ratnashri. Yeah.
I'm ending the broadcast.